So in today's lecture, we'll talk about Poisson data example. We'll continue discussing Poisson data example. Then go to exponential data example. If time permits, then we'll talk about credible interval. And we are on chapter 3. So the example that we are talking about is the number of blemishes in a film, right? In a film, number of blemishes we are recording. That was the problem. And we wanted to figure out Jeffrey's prior distribution for our problem. So what was our problem? I gave you this problem that what is the data set? Okay, so maybe the data set is given right here. Okay, so this is the data. Suppose that we have the following data over a period of 50 hours from the film process. Analyze the data using the Bayesian and frequentist method. Frequentist means the classical method. So what you have blemishes, number of blemishes found, and every time it was sampled certain square centimeter area. So suppose on the first occasion, it took a sample of 8 centimeter square area and found 3 blemishes. Next instance, it sampled 9 centimeter square area and found 2 blemishes, so on and so forth. So you have 50 hours. For every hour, the process took a sample of certain areas of that film process. So theta, what is our interest? Our interest is in estimating theta, the number of blemishes per square centimeter. So over an area of W square centimeter, the number of blemishes follows the Poisson distribution with parameter W times theta. If we assume the number of blemishes per square centimeter follows a Poisson distribution with parameter theta, then over area W centimeter square, it will again follow a Poisson distribution with parameter theta times the area of the film. This W is referred to as the offset term. For this problem, let Y be the observed number of blemishes over W centimeter square. Then the likelihood and the log likelihood are the following. So the likelihood this time, Y given theta, is the probability that the random variable takes value Y. It is e to the power minus W theta times W theta to the power Y over Y factorial. And this Y is what? This Y could be 0, 1, 2, anything, right? Now, why I write it in this way? Because first, I want to derive Jeffrey's prior for this problem. Therefore, I need to write down the probability model, which will give me the likelihood function. So the likelihood function for a single observation is log of this guy. In the previous lecture, we talked about that it does not matter whether we take all n observations or we take a single observation, the Jeffrey's prior will be the same, right? Therefore, I'm doing the calculation based on a single observation. So log py given theta will be minus w theta and y times log of w theta minus log of y factorial. So separate out theta. So this will be minus w theta and y. So this is a typo. This should be capital Y, not the little y. Capital Y times log of w and again capital Y log of theta minus log of Y factorial. You know the technique of deriving Jeffreys prior. First, you take double derivative of the log likelihood, put a negative sign, take expectation, and that is the information. Then take the square root of the information, will give you the Jeffreys prior. So first derivative of the log likelihood is minus W plus Y over theta. Second derivative is minus Y over theta square. Thus the Fisher's information is negative of the double derivative and expectation. So you take expectation of this guy, Y, right? That is the random variable. You take expectation on the random variable. Theta is the unknown parameter, but in the expectation calculation, theta is treated as a constant. So it will come outside. Expectation is on the random variable. And expectation of Y is expectation of Y is the random variable, is here is a typo. I made a typo. It is, remember, for this problem, it is W theta. W theta. So it should be W theta. I will correct it. W theta over theta square. So it is 1 over theta. Now, not over 1 over theta, it is W over theta. Okay. So the Jeffreys objective prior is P theta proportional to square root of the information. Square root of the information will be this theta in the denominator, and square root of it will be theta to the power minus 1/2. Let me write it. What happened to that W? I said W is the offset term. It's a constant, right? So I can write it with the proportional sign and remove W. So information, expectation, and this is theta times W over theta square. So 1 over W over theta. Next, the prior distribution P theta is proportional to right. So again, I can write it as proportional to this, right? 1 over square root of theta. I will give all the theta related terms. Anything which is multiplier, I can put that in the constant of proportionality. And this is theta to the power minus 1/2. So what it shows is that whether you work with the offset term or not with the offset term, Jeffreys prior remains the same. Jeffreys prior for the Poisson distribution is theta to the power minus 1/2. Okay, so this is this, and for working with this problem, if you use Jeffreys prior, then you will be multiplying your likelihood with this prior distribution, then obtain the posterior distribution, and then make inference. Now, one other type of prior is the mixture prior. If f1 theta, f2 theta, fm theta are all proper densities and k1, k2, km are such that they all are greater than equal to 0 and their total is 1. So we can think of k's are weights. Then p theta, the density function, which is written as sum of k sub j times fj theta, is a proper density and called a mixture prior. It is a mixture of several probability density functions. And the mixing weights are those things, K1, K2, Km. Now here is one example. Show how the 10:8 mixture of normal distribution and normal 0,1 distribution and normal 3, 0.25 distribution look like. It is important to understand that this mixture distribution is not same as the distribution of 10/18 times x1 plus 10/18 times x2, the weighted average of two random variables where x1 follows normal distribution and x2 follows this normal 3 and 0.25 distribution. Okay, so what I'm showing you, this is just an example and clarifying some of the confusion that you may have. Is that suppose you have a 10:8 mixture of the two normal distributions. How does it look like? Ten is to 8. So it will be 10/18, right? Normal density D times. So I'll write a function and I'll show you the density function of this mixture distribution. F1 is a function, okay? Function of X argument. And it is d norm of x comma 0 comma 1. D norm is the syntax used for the normal density function in R. If you want to use some other language, Python, there is a analogous function or syntax. And it is 8/18 times d norm x3 comma 0.5. For f1 from -3 to 5. Okay, let's see. Oh. So this is the mixture of the two distributions looks like. And what about this guy? What about this guy? 10/18 x1 and 8/18 x2, where x1 follows normal 0,1 and x2 follows normal 3, 0.25. What is the distribution of this guy? Is it same as this mixture distribution? No, this is not same as this mixture distribution. Rather, the distribution of this is a normal distribution, right? Because it is a linear combination of two normal random variables. So it follows a normal distribution, and its mean and variance we can calculate it easily. So let us say y equal to 10/18 x1 plus 8/18 x2. Okay, x1 and x2 are independent. Let's say x1, x2 are independent. and x1 follows normal 0, 1, and x2 follows normal 3, comma 0.5 square. So why? Because it is a linear combination. Of Gaussian random variables. So y follows. It only happens if they are Gaussian. If they follow something else, there is no guarantee that it will follow the underlying distribution, same distribution. So y follows normal distribution with mean same as 10 over 18 times the mean of x1, which is 0, and 8 over 18 times the mean of x2, which is 3. And the variance will be 10 over 18 squared times variance of x1, which is 1, plus 8 over 18 square times variance of x2, which is 0.25. And because we assume they are independent, I do not need to worry about the covariance term. Okay, so this is the variance. This guy is the variance of y. So you see, this is purely a normal distribution, and over there, that was mixture of two densities. Next, the posterior distribution of the parameter corresponding to the mixture prior is the following: P theta given data, data is denoted by y in this lecture note, will be again weighted mixture of two multiple density functions, and the density function, each density function, how do you obtain that? So I call this mixing density as f tilde j, which is fj theta times the likelihood. So this is the, remember, jth component of the mixture prior, fj theta times this likelihood divided by a constant Cj. This normalizing constant Cj is the integration of fj theta times this data distribution given theta, and you integrate theta, Cj theta. And what is that k tilde j, which is the mixing weight of the mixture posterior distribution, which will be k sub j, which was the mixing weight of the prior of the jth component, Cj over C, and C is sum of Kj times Cj. So if you don't have a mixing prior, things are relatively simple. But when you have a mixing prior distribution, then finding the posterior distribution is slightly difficult, because it requires you to calculate the normalizing constant C sub j in order to calculate the mixing weight of the posterior distribution. So the bottom line is the posterior distribution is again a mixture distribution, and the weights, mixing weights are updated. Mixing weights are not simply Kj. This is one thing we try to think, that mixing weight of the prior distribution is Kj, K sub j. For the posterior distribution, it will still be K sub j. No, that is not true. It will be updated. So here is the example, and no innovation in mathematical innovation here. Now I'll talk about the real data example, apply the real data example. I'll apply the methodology to the real data example and get the results. All code is given here. You try on your own. Just copy and paste the code and get the results. So this is blemishes and the area. For the ith instance, the number of blemishes yi over the area wi follows Poisson distribution with parameter wi theta. This is the solution. Now, what the solutions? First, I said analyze the data using the Bayesian and the classical method. So, first, we'll obtain the classical point estimate. The likelihood of y1, y2, yn. What is that n? N is the number of instances when you calculated the data. So you have 50 such instances, 50 hours of data. So n is 50 in your real data example. The likelihood function is the probability mass function evaluated at every hour, evaluated at the data collected at every hour, and then product over I is equal to 1 to n. And if you do that, this is just an algebra. It is e to the power minus theta and sum of wi, theta to the power n times y bar. And this guy, I wrote this guy in red to signify that it is free from theta. So in your derivative or any other calculation, this part will not contribute anything. Therefore, I wrote the next line as the proportional, ignoring the term involving data, only data. So e to the power minus theta times y wi and theta to the power n times y bar. How do you obtain the MLE? First, you take log of likelihood. So L theta, which is log of this entire guy, this guy, ignoring the constant term. And the first thing you take derivative, we call it score function, derivative of the log likelihood. So when you take derivative of this term, it is simply minus wi, and the second term is n y bar over theta. MLE is obtained by solving this equal to 0. So you set the score function equal to 0 and solve for the unknown quantity. So theta hat is equal to n y bar over sum of wi. Now, although I said this is how MLE is obtained, there are some intermediate steps. For example, this is the solution of the gradient equation. How do you know that this is the solution that maximizes the likelihood? MLE means maximum likelihood estimator, right? So the argument of the parameter that maximizes the likelihood surface. So the gradient equation solving is not enough. Next step is you check whether it gives you the second derivative negative value at this solution. So I omitted those steps, but those steps are there. You take the second derivative, evaluate the second derivative of the log likelihood at this value theta hat, and check whether the second derivative is negative. And that is your complete solution. Next is the Bayesian inference. So I gave you the classical estimator, but I have not talked about how to calculate the standard errors and other things, because if I do that, that will take me to the entire other route. So I just stay away from that detailed calculation, go to the Bayesian part. In the Bayesian inference, what I need a prior distribution for the parameter. Theta is the unknown parameter. So assume theta follows the gamma distribution with parameters A and B. So the posterior distribution, theta given data, is the likelihood times the prior distribution. And the likelihood part is this much. And the prior distribution, gamma prior, gamma A comma B, means theta to the power A minus 1 times e to the power minus B theta. Now, some people prefer writing b in the denominator. So that is also possible. You can write um, the prior density as theta to the power a minus 1 e to the power minus theta over b. Both writings are correct. Just understand the interpretation. So gamma, so theta, if I say theta follows gamma A, B, where B the rate parameter, then F theta, not F theta, P theta will be proportional to theta to the power A minus 1 e to the power minus B theta. Now, if I say theta follows gamma A comma B, B the scale parameter, then P theta will be proportional to theta to the power A minus 1 e to the power minus theta over B. So depending on what you want, in my homework or in my exam, definitely I'll specify B, what that B uh, stands for, whether it is the scale parameter or the rate parameter. But here it is the rate parameter, so it is written in this format: B times theta, and collecting all the terms involving theta, you obtain theta to the power n y bar plus a minus 1 and e to the power minus b plus sum of wi times theta. So it is a gamma distribution again with shape parameter n y bar plus a and the rate parameter b plus sum of wi. If you want to use Jeffrey's prior, then the prior is, you can think of it is a gamma distribution with shape parameter 0.5 and the rate parameter 0. So if you just plug in b equal to 0, after plugging b equal to 0 and a equal to 0.5, you get the posterior distribution to be gamma in y bar plus 0.5 and the rate is sum of wi. Now you have the numeric calculation. So what was the maximum likelihood estimator? Maximum likelihood estimator was sum of blemishes divided by sum of area. Sum of n y bar means what? Sum of n times the average blemishes, right? Means a, it means it is sum total of yi. And in the denominator, it is the total of all areas. So sum of blemishes divided by sum of area. If I use gamma 1, 1 prior distribution, then the posterior distribution will have shape parameter 1 plus sum of yi and the rate parameter 1 plus sum of area. And what I did, I created this function f1. F1, this is the function, d gamma function. This is the density function, and then plotted it. So this is your posterior distribution. This is how the posterior distribution look like. Okay, this is the gamma distribution with shape equal to this and rate equal to this. And then I used other prior distributions such as gamma with shape parameter 10 and rate parameter 1, so on and so forth. And then lastly, for the Jeffreys prior, where gamma equal to 0.5 and 0, and the posterior was this. So once you get the posterior distribution, what can you do? You can calculate the posterior mean, posterior median, posterior mode, depending on what you want to calculate. And you can calculate probability that theta is greater than something under that posterior distribution, or theta is smaller than something under this posterior distribution. You can do that calculation. For instance, and you can even calculate 2.5 and 97.5 percentiles of the posterior distribution. So let us do that. For this posterior distribution, I can calculate Q gamma and 0.025 and 0.975. They are 0.24 or 0.25 and 0.34. So what is the meaning of that? The interpretation of these values are the following. So probability theta lies between 0.25 and 0.34 given data. So the posterior probability that theta lies between 0.25 and 0.34 is equal to 0.95. This is the interpretation. You can calculate even a median. For median calculation, we set this Q gamma to be 0.5. The median value of this distribution, posterior distribution, is 0.29. And what was the maximum likelihood estimator? It was 0.291, and this one is 0.2917. But the beautiful thing is, the beautiful thing is, you can have this credible interval, not the credible interval, and a nice interpretation of the credible interval. You can say theta lies between 0.25 and 0.34 with probability 0.95, posterior probability. That type of nice interpretation is not available in the classical confidence interval. Classical confidence interval requires you to invoke the hypothetical population. It tells you, suppose you get the confidence interval, 2 endpoints of the confidence interval. It does not tell you whether theta is within that interval with certain probability. For example, you get the confidence interval . suppose the 95% classical confidence interval for theta is, let's say, 0.23 and 33. But you cannot say that theta lies between 0.23 and 33 has a probability of 0.95. You cannot say that. How you interpret the classical interval? Classical interval are interpreted as follows. Suppose you repeatedly draw samples from the underlying population, and every time you calculate the confidence interval using the formula that you have used to calculate this value, then 95% of the time your interval will contain the true parameter theta, and 5% of the time it will not contain the true parameter, but it cannot say what happens to this particular interval. Okay. For this particular interval, either it contains or it does not contain, but we do not know. But the procedure guarantees that 95% of the time the interval will contain the true parameter. The procedure guarantees. Same thing. When you listen to the weather channel, weather channel tells you that there is a 20% chance of rain. Okay, 20. What is the meaning of that in today's context? In today's context, today there is a 20% chance of rain, but in the end of the day, either you have rain or you don't have the rain. Like here, either this interval contains theta or it does not contain theta, right? So how will you associate the probability? So the probability is associated if the experiment is repeated multiple times. Same thing, weather channel tells you if you observe same weather condition as of today over many days, then 20% of those days will have rain. But for today, I don't know what would happen. So this is the difficulty, little bit difficulty I find of interpreting classical confidence interval. Here, Bayesian interval, very easy to interpret because you can directly tell me that theta lies between 0.25 and 0.34 has a probability of 0.95 given the data. All right, so now coming back, questions. Now we'll do for the same problem, Bayesian inference with the mixture prior. So far we talked about Bayesian inference with the gamma prior, different A and B, and the Jeffreys prior, now the mixture prior. So let the prior for theta is a two-component mixture, and the components are both of them are gamma distribution, gamma A1, B1, and A2, B2, and these are the mixing weight K1 and K2. Now for the mixing prior, you see, I had to write the entire prior density completely with the proportionality constant. Previously, I omitted writing those things, but this time the calculations are messy, therefore I keep all the terms. Otherwise, I may end up having wrong answers. Then the posterior is again a two-component mixture. So first component again is a gamma distribution, and just taking this part means theta to the power a minus 1 and e to the power minus b1 theta mixed with the likelihood part gave me the posterior distribution, and that posterior was this guy. And here I wrote all the proportionality constant. Okay, here also. And for the second component, taking this thing, this part, kernel part, with the likelihood part, I got the posterior distribution. I wrote it here. With the mixing weight K1, now I call it K1 prime and K2 prime instead of K1 and K2. And K1 prime is K1 times C1 over C. K2 prime is K2 times C2 over C. And what is that C? This C is K1 times C1 plus K2 times C2. C1 and C2 are the marginal likelihood part. C1 is the data given theta and multiplied with P1 theta, the first mixing component of the prior distribution, integrate theta from 0 to infinity. When you integrate theta from 0 to infinity, and it looks like a gamma distribution. So gamma integration, you apply the gamma integration, and you get this following formula. Now things are very easy in this context because you know the gamma integration, you apply the gamma integration formula. Things are not simple if you use some other distribution. Okay, so if you use some very odd looking distribution, then obtaining C1 is very difficult. Oftentimes it happens. We have to use something else, something other than gamma or known distribution, and then calculation of this marginal likelihood is very difficult. And this is one of the research topics in Bayesian inference. How do you calculate this marginal likelihood? Here, it is relatively simple because you have only one parameter. You are integrating one parameter, theta, and that integration can be done numerically using several numerical quadrature formulas. But when you have multiple parameters or a vector of parameters, then numerical quadrature will not give you a good result. And the error of approximation increases with the dimension. Then what do you do? So then people use Monte Carlo method to calculate that type of integration. So this is nothing but integration without Bayesian thing. This is simply an integration with respect to a parameter. And the problem is often you don't have the analytical form like I have of this integration. So Monte Carlo integration is the topic of chapter 4, next chapter. C2, the other constant, is also obtained like this, and you obtain this formula. So K1 prime equal to K1 C1 over K1 C1 plus K2 C2 becomes the ratio of this guy to this entire thing. So numeric example, suppose I have the following mixing distribution as the prior for theta, and it is 1:9 mixing of two gamma distributions, gamma 1, 10 and gamma 2, 2. So what would be the posterior distribution? The posterior distribution will again be a mixture of two gamma distributions, and the mixing weights are calculated using the formula given here. And I calculated that. So this mixing weight term 1 over term 1 plus term 2. Okay. So this is the calculation. And it turned out that it is the mixing weights are 858. So I actually calculated the weights, mixing weights came out to be 858 over 858 plus 9142. Weight for one component. The weight for the other component is 9142 over 858 plus 9142. If you do the calculation up to this line, you will get the value of 858 and 9142. Then what I did, this is a gamma distribution, and I showed you how you can generate data from this gamma distribution. You can, if you want, you can draw the gamma density function, mixing density, the way I did it for the normal mixing density, no problem. But here I show you how you can sample from this distribution and draw the histogram of those samples. That will give you the idea about the underlying posterior distribution. Why? Why did I not use the formula to draw the posterior distribution? Because often you will not be able to use formula. Often you have to rely on the samples drawn from the posterior distribution and use those samples to draw the histogram to get the idea about the underlying posterior. So I simulated data, my simu data I call it, is I have simulated 858 gamma random variables from this distribution and 9,142 gamma random variables from this distribution, and then create the histogram. Questions? You have the code, copy, paste the code, understand what is going on. Bayesian inference with a mixture of gamma distributions as the prior still continues. Now let us calculate the posterior mean for theta. So essentially I'm talking about posterior mean for theta means calculation of the average value of this mixture distribution. So theta times the posterior density function, which is a two-component mixture, is like this. So first we calculate the posterior mean of the first component. It turned out to be this, multiplied by the mixing weight, and then the posterior mean of the second component multiplied by the mixing weight. Next, let us calculate the posterior mean for theta using the analytical formula. So here you have this analytical formula, apply that. So we use that analytical formula, came out to be 0.2932. Next, also numerically calculate the posterior posterior mean, I forgot to write, mean, median, standard deviation, the 95% confidence interval of the posterior distribution. You have already the sample data from the posterior distribution, calculate the mean value, came out to be 0.2933, which is different from the analytical formula. Analytical formula is the theoretical one, right? And this is a numerical one, but this is a very close approximation. They are not identical. Of course, they will not be identical because this is based on your finite sample. You have drawn maybe 10,000 observations from those, from that distribution, posterior distribution, to approximate your mean. Approximate does not mean you get exact value. You get somewhere close. So you get the mean using the numerical approach. And this is most relevant in the practical setup. In most practical setup, you don't have the analytical form. It's very difficult to obtain the analytical form. So you rely on the posterior samples, then use the posterior samples to calculate mean, median, mode, or any other probability. Median came out to be 0.2924. Standard deviation of the distribution came out to be 0.0239. And I also calculated 2 percentile points of that posterior distribution. One is the 2.5th percentile, another is 97.5th percentile, came out to be 0.248 and 0.342. Now 0.248 and 0.342, look, previously we also calculated the 95% credible interval based on gamma 1 prior distribution. This time we calculated the credible interval based on this mixing prior distribution. They are very close. All right. So yeah, you all have a nice weekend. We'll talk about the credible interval in our next lecture.